Let's get started. Thanks a lot for joining this session. I hope you enjoyed. If you are looking for a silver bullet to solve this problem, sorry, I'm going to disappoint you a bit. There are no silver bullets, but yeah, let's discuss a little bit this issue and try to find out solutions for it. The motivation for this talk, I had a customer some time ago that was having this problem, and I looked for references on this issue, and I could not find any. Maybe there is something out there, but I could not find a good reference on this topic, right? On what kind of step-by-step you should do to design a system that is power cut resilient. So yeah, I decided to just create one talk about it. This is something that over time we have to face it. So yeah, I hope you enjoyed. My name is Sergio. Work with embedded systems for almost 30 years now. Started work with Z80s in the past, and yeah, moved to Linux in the 90s, and yeah, work with Linux and open source for some time now. I have my company located in São Paulo, Brazil, and I do consultancy and training on several different embedded Linux topics. Also have some contributions on the Octo, Linux, Buildroot, and other open source projects. Sort of easy to find me on YouTube, LinkedIn, and other social networks. So yeah, first the problem. What can happen if you just turn it off an embedded Linux device? Of course, you would stop everything, right? So any in-progress operation would stop. That means you might stop in the communication with peripherals. You might stop in the control of motors, let's say, for example. You might cause peaks in the voltage that might even damage the hardware. And of course, you might corrupt the file system, lose that data, right? So those are the consequences, some of those consequences of removing power from a running system, right? And the main focus of this talk is on file corruption. So that's my main idea here, to talk about mitigation techniques to try to minimize data loss and also file system corruption. But of course, most of the mitigations that we're going to see here, they could be applied, and other use cases could benefit from that as well. I also don't plan to cover other situations that can cause file system corruption, right? For example, bit flips in NAND flashes, right? So I'm really focused on power cuts here. And it's also important to mention, and I'd like to mention this in the beginning of the talk, there are always trade-offs, right? For every mitigation that you decide to implement, you're going to have trade-offs. Could be additional hardware costs, right? You decided to add a battery, a supercapacitor to the hardware. You might reduce the performance, right? You might increase the wear, you might do more writes on the flash, which is bad, right? Decreasing the lifetime of the flash. You might increase development time, maintenance time, the software will be more complex. Those are all the costs, right, for implementing some mitigations. And you always have to think about, right, the cost benefit of a mitigation technique. This is important to mention. I would say there are 3 steps to work on this problem. You have to reduce the probability of the problem to happen or to have bad consequences when it happens. And you have to have a mechanism to detect when it happens. And if it happens, try to recover from it. So those, I would say, are the 3 main steps for this. We're going to cover all of the steps during this presentation. For reducing the probability, I would say we have 3 layers to work on. We have to work at the hardware level, or might work at the hardware level to solve this problem, at the operating system level, and at the application level. It's like security. You have a layered solution that you have to think about all of the layers when trying to solve this problem. So that would be my approach for this problem. You need to implement, I mean, if you really care about this, you need to have some mitigations at the hardware level, operating system level, and application level. And together with this, you have to detect and recover if you have problems, right? Let's talk first about hardware level mitigations. Also important to mention here, I want to touch several different topics that could be a talk on itself. So I cannot go really deeper on a specific topic. That's why we're gonna just scratch the surface on most of the topics here. And of course, when you are working on your project, you might want to go deeper onto a specific topic. At the hardware level, those I would say would be the main mitigations. First, make sure you have input protection on your power supply. This is very important. Avoid spikes in the power source to avoid damaging the hardware, for example. And some spikes could even reset the hardware, and then that could be bad. Add a battery or a supercapacitor to hold the power just for a little bit, so you can handle, like you can shut down the system gracefully. That could be another mitigation technique. Using a power management IC, most SoCs nowadays require a power management IC, though, so that's not an issue. And some of them have this detection, you know, when the voltage is low, and then can notify the operating system on that, and then you can take some action. Together with, for example, a supercapacitor, you might have some time to handle this, you know, sync the disk, send some message, I don't know, send a command to the eMMC controller to flush the cache before shutting down. We're going to talk about this during the presentation. And also, when you are selecting the storage device, you need to select one that is industrial grade, right? That has some kind of capabilities to identify a power loss and handle it. There are even some interesting features inside an eMMC, for example, that you can enable and use it during a design. I'm going to mention a few of them. So those I would say are the main topics that we need to care about if you are designing the hardware. Here I have a few pictures, like this is a power management IC from NXP. We have there some power good signals that could be connected to the processor, and then you will be notified if the power is good or not and take some action on it. This is a circuit from a design note from analog devices on a supercapacitor, like you have on your left supercapacitor charger circuit that will charge 2 capacitors, and on your right you have a DC-DC converter. And this could be connected to the power management IC to power the system in case of the power is cut, right? And according to this design note, you have 20 watts of energy for 1.5 seconds, which might be enough for you to do what you need to do, right? To gracefully shut down the system. Again, trade-offs. There are hardware costs to do this, right? It really depends on your use case, on the reliability you want for your system. This is a snippet of a data sheet from an eMMC vendor, Smart Semi, and there you can see power loss detection. Whatever that means, I think one of the problems with eMMCs is that they are black boxes. We don't really know how they are implemented, right? We have the data sheet, we have to trust it. According to this one, we have power loss detection. Usually, most industrial grade eMMCs, they have a small capacitor to hold the power, so it is able to detect a power loss and then flush the caches so you don't lose it. And that's one important thing. You have caches inside the eMMC. You not only have caches in the kernel cache for disk writes, you also have caches in the eMMC. So if you turn on the device and the device was not able to flush the caches, its internal caches, you might lose that data, or maybe corrupt the file system. If you are working with an MMC, you can you can disable those caches if you want. So there is an interface in /sys. There is a knob there that you can just write it, a file called write cache for each eMMC device. It's by default write back, which means it is the cache is enabled. You can disable it by writing write through. So you disable the cache from the eMMC controller. This is not a cache from the kernel, from the eMMC controller. You're losing performance here, right? You might increase writes as well. So those are the trade-offs. If you want to live with it, you can do this. There are two additional features that you can have, like this is in the JDEC standard, the standard for eMMC, called enhanced area and write reliability. Does anyone know about those? Who knows about those features? Nice. Sometimes people confuse, like there are two different features that you can use from recent eMMC controllers. To understand a bit how this works, you have to understand a bit how a NAND flash works, right? You have cells with one or more bits inside of it, and then the cells are organized in pages, and pages goes to a block, which is an erasable unit, right? So you erase blocks with pages, but you read and write to pages. You have SLC NANDs, MLC NANDs. So SLC NANDs are NANDs with just one bit per cell. They are usually more reliable. When you are working with MLC NANDs, they are less reliable because of the iris build. So usually what happens is that you have, for MLC NANDs, you have, like, let's say you have 2 bits MLC NAND. So you're going to have 2 logical pages that builds a physical page. And 1 bit, like for every cell, 1 bit goes to one logical page and the other bits go to the other logical page. They are paired. And when the eMMC controller is writing to the flash, what can happen is, if you are reading or writing from one of the paired pages, the other page might flip bits. So you might have those kind of bit flips. Those features try to minimize this kind of situation. So for example, the enhanced area feature, it will basically change an MLC NAND to SLC NAND. They call it a pseudo SLC. That means instead of using the 2 bits, it's going to use just one. Actually, it's going to, the 2 bits will have the same value. So in practice, they will only assume 0 or 1. So it's handling multiple bits as a single one. This will increase a little bit the endurance and reliability of the flash. The cost, of course, is the storage. You're going to decrease basically in half, right? Let's say you have an MLC NAND. For every 2 bits, you're just handling as 1. So you're decreasing your capacity by half. That's the cost, basically. You can enable this feature if you want and increase reliability by just using an MMC command from the MMC utus package. There is another feature called write reliability. It's a little bit different. And it's implementation defined. I mean, it depends on how the vendor implements this. But usually they use some kind of backup mechanism when writing to a page. So you always have like a page and a backup of it. And it does in an atomic way. So you will never have like pages written in a half, let's say, right? So you always have the old value or the new value for that page when you enable this write reliability feature. That, of course, has also costs. For example, you increase the number of writes, which will decrease the lifetime of the flash memory. The performance will go down a bit as well. Sometimes vendors provide numbers on this, like if we enable write reliability, we'll decrease the performance in 20%, for example. This is a data sheet from a Kingston eMMC that talks about those two features. The enhanced area, that's the first one there, the talking about the PSLC mode, and reliable write at the bottom. So if you look at your eMMC data sheet, you're going to find similar information, right? Especially for industrial grade eMMCs. And of course, I'm talking here about eMMC because that's almost embedded Linux designs nowadays. We use eMMC, right? But if you are working with a different storage device, right, you're going to have to go after those kind of information, right? Let's say you are designing with an SSD, right? Which is similar, but not the same. So keep that in mind. This is a command from the eMMC UTILS package where you can see like how can you enable those features. And I didn't mention, but when you do this, the process is irreversible. You cannot change it back. Keep that in mind. All right, so those were a few examples of mitigations at the hardware level to improve the reliability, right? With a focus on writing to the storage. Let's talk now about the operating system. So at the operating system level, there are a lot of things that we can do to improve the reliability and recover from power cuts. The first important thing, and I mean, there are lots of, let's say, for those that work with embedded Linux for a while, most of those techniques are common to all of us, right? Define a robust partition layout, very important. I'm going to discuss a little bit about this. Select the appropriate file system. There is no like real right decision here, right? You're going to have to, again, think about the trade-offs, for example, on using ext4 or F2FS. When you're mounting the file system, think about the options that you can pass to mount it. There are a few interesting options, especially for reliability on power cuts. And yeah, have a safe and reliable update mechanism. That's also, I would say, part of the solution. Good practices for partition layout, in my opinion. First, super important, separate read-only from read-write data. So whatever can be read-only will go to a read-only partition and read-write to another partition. That's why you should always have your root file system in a read-only partition. Because you are not writing to it, so the possibility of having some kind of corruptions there is very minimal. I'm going to discuss a bit about file systems for this, but have always the rootfs as in a read-only partition, and whatever you need to persist, writable data is going to go into another partition. And for writable data, separate volatile and persistent data, always, right? So the idea here is to minimize writes, to avoid losing data, to avoid corrupting the file system. So whatever can be volatile, you go to RAM. We're going to use TMPFS for that. And for persistent data, also separate critical data from everything else. So it's a good practice. You have to store logs which are not critical, do it in another partition. For critical data, let's say config files, databases, is going to be in a separate partition that you're going to really manage. Like you don't care much about the logs. If you lose a log, you don't care, but you don't want to lose or corrupt your database. And also try, if you can, right, if you have enough space, duplicate partitions. That will be really helpful maybe if you want to recover from a corrupted partition. If you have two, A and B, then you can try to recover from a corrupted partition. I'm going to talk more about that later. There is a recommendation from vendors. Who here have heard about over-provisioning? Right. So there is a recommendation from vendors of devices with FTL, right? The flash translation layer, so eMMC, SD cards, SSDs. There is a recommendation for you to provide some, to leave it available part of the storage for the device itself. This is called over-provisioning. So you don't use everything. You don't use everything, format all of the partitions, and use all of the storage. Leave from 10 to 20% available, unformatted, unpartitioned. So the controller from the MMC, for example, can use that for internal operations. The controller does a lot of operations, garbage collection, wear leveling, a lot of the kind of stuff. And there is already actually some over-provisioning on the device itself. That's why you buy a 32 gigs SD card and it reports to operating system 29, not 23, because there is some over-provision. The device uses part of it for its internal operations, moving like bed box management, wear leveling, that stuff. And some vendors say you should even have some user-defined over-provisioning to improve that. That will improve reliability and even performance. This is a paper from Samsung on some tests they have done on SSDs, but not embedded in the cloud, where when you have over-provision enabled, you have a better performance from the SSD. I don't have data about eMMC, if that really improves eMMC or not. But yeah, it really depends on how the controller is implemented inside the eMMC. You might want to do some tests to see if that applies to you or not. Having a read-only rootfs is really a good technique for mitigating the risk of corrupting the file system, right? Because the only thing that you really don't want is your root file system corrupted and you cannot boot your operating system anymore. The two most common file systems for that are SquashFS and HeroFS. SquashFS is a very known file system. HeroFS is a bit like newer, right? It was created, I think, by Huawei for Android. It's been using a lot in Android nowadays. On the embedded side, I've used SquashFS, I don't know, in the 20s when I worked with routers a lot. So it's a very known and old, but yeah, one of the best options that we have for a read-only file system. What is nice that compress the data, so it's not only read-only, but you have compressed data, so you have more space available, I mean, because the data is compressed. The difference between them is a sort of a trade-off between the compression rate and the read performance. HeroFS doesn't compress that much, but it's better when reading data. The performance is better, so the decision might be between those two trade-offs. And another option would be to just use a writable file system like ext4 and mount it read-only. That's an option as well. The problem with that is that who knows who is working on your system, and they can just remount it, read-write, and do some stuff there. So I would not recommend this. If you really want a read-only file, you should really use a read-only file system. But sometimes you need to write to the file system. So I usually have two approaches for this, right? You can create links to a writable partition. That's one option. Let's say you want to write to /tc/ssh. You can link that directory to a directory inside /config, which is mounted in another partition, and then you are able to write to that. So we have a config partition with your configuration and some links from etc to this config partition. Then you can manage much better the changes that you are doing in the root file system. Another option would be to use an overlay file system like overlay FS. On the reliability side, I don't like that much because with overlay FS, you can overlay every part of the file system, don't have control over it. So you can overlay binaries, for example, and if you overlay like an application from the root FS and then that partition is corrupted, you cannot maybe boot the system or run the application anymore. So I would not prefer, for this specific use case, when you want reliability on power cuts, I would not recommend overlay FS because I don't want to write and replace important files from the operating system. Having links would provide you a more controllable environment, let's say, for changes in the root FS. And for data, there are multiple file systems that we can use, right, to store data. I don't plan like to cover in detail every file system. I don't have time for it. We could have a specific talk on each of those file systems, and we do have actually, like, if you look at YouTube, you're going to find several talks on how F2FS works and how UBIFS works and so on. So I plan to just comment a bit about it with a focus on power cut resilience. I mean, for conventional hard disks, which is not common embedded, we have XT4 and B3FS or ButterFS or whatever you want to call it. Those are the most common nowadays file systems. For hybrid devices, those devices with NAND flash and FTL, like eMMC, I would say nowadays the two good options for the file systems are XT4 and F2FS. I'm going to talk about both. ButterFS, B3FS is also a possibility. I have never tried B3FS on eMMC and on embedded use cases. Have anyone? Does anyone have experience with B3FS? Nice. Maybe we can talk later. Curious about your experience on this. But yeah, I haven't used B3FS on any of my embedded Linux projects yet. So I cannot comment on it, right? For high-end devices, I mean, the main file system is UBIFS that runs on top on UBI. I'm going to mention a little bit of it. And we also have JFFS2. It's a very old file system. It's an alternative, but maybe only for very small flashes. XT4, it's one of the best alternatives for the MMC. It's a journaling file system. That means it creates a journal on every write. It can journal data or metadata. Actually, metadata is always journaled by default. You decided if you want to journal data or not. And the journaling mechanism is the solution to avoid corrupting the file system, right? So here is a diagram where, I mean, journal is pretty much, on Linux developers, right? So for every write, you journal in the disk what you want to do, and then you do the write and erase the journal. When you are booting, you check the journal. You discard incomplete entries to the journal. That means you might lose data. Journal will not prevent you from losing data. But the idea is that you will not corrupt the file system, right? So if you have entries in the journal, you replay them. That's the main idea for journaling file systems like XT4. There are in XT4 3 journaling modes: ordered, write back, and journal. Ordered and write back is similar in the sense that they just journal metadata, but they are different in a sense that in the ordered mode, it will make sure that the data is written before the metadata is journaled. Because if you do the opposite, which is the write back mode, if there is no ordering, you might write metadata before data, and then your file system will corrupt because you might, your metadata might be pointing to some data that doesn't exist yet. So usually the order mode is one of the recommended modes, right? If you don't want to journal data, you enable the ordered mode. It will make sure that you have metadata journaled, but you have the data written before creating the journal for the metadata. Now we have a light. Now we don't. That's a power cut. Hopefully, nothing was corrupt in this process. There is the journal as well mode where data and metadata are journaled. Of course, you're going to have more writes. If we're talking about flash-based devices, you're going to decrease the lifetime of the flash. You're going to wear the flash faster. Always think about this, right? But for example, let's say you have a tiny partition with config files that doesn't change much. It makes total sense for me to enable the journal mode because you're not writing that often, right? Just to change a configuration. So you'll not really impact the wear in this specific case. So you might have partitions mounted with the ordered mode where you write lots of times and partitions mounted with journal, for example. Those are a few extra mount points that you might think about and specifically for have some resilience on power cuts. You are going to always to use no access time. To avoid the operating system from updating access times to files. This is very important because, I mean, if you are in a writable partition and you CD to this partition, you're going to generate a write. If you read a file, you're going to generate a write because every file has metadata about the latest date and time access. So for flash-based devices, you might want to disable this because you don't want those extra writes. And also to avoid corrupting the metadata, right? Because that's the main rule here. The less you write, the better. So whatever you can avoid writes, the better for this use case. There is other mount options there as well. Maybe I can comment on a few more of them. I already comment about the data equals journal, right? When you want to journal everything, data and metadata. I would do that for critical partitions, right? Maybe databases, maybe config. Just think about the trade-off. You're going to increase a lot the writes because you're going to be journaling data as well. You can configure the frequency of the syncs to disk with this commit option. I would not really recommend the sync mount point because it really increases the write, and I don't think you need that. You can control the syncs via software, for example, calling fsync. So I would avoid the sync option. Although it is there, it is important to know, right? With this sync option, you don't have caches in the kernel, right? You don't have cache writes in the kernel, so every write goes directly to the device. I would avoid that if possible and try to control this via the application. F2FS is a file system created by Samsung, specifically for Android. I have used it already in a few embedded Linux devices, and it's working so far very well. It's a log structure file system, differently from ext4. So it's a kind of log. It keeps writing in a log form. So it never, like when you want to update a file, it doesn't change the file, right? It writes into a new it writes like it follows a log, so it keeps writing into a new like block if needed, and the old block is initialized. So in the end, it avoids like write amplification because you don't have to do like those in-place updates. In the end, it's better structured for flash devices compared to ext4 that was not really designed for flash-based devices. It has a garbage collector. I mean, I don't want to go over these details, but one important detail is the checkpoint system, because that sort of replaced the journaling system from XG4. That's the way they handle the consistency of the file system. So by default, 2 checkpoints are maintained. The current one, the previous one. And when the system is booting, it boots from the latest valid checkpoint. So if for some reason you are writing to the file system and something happens during that process and it was not able to finish the write and create a checkpoint for that write, at the next boot, you're going to boot the old checkpoint. Of course, you might lose data. You cannot avoid that. But you're not going to corrupt the file system. You're always going to have a good known state of the file system with this checkpoint mechanism. BTRFS has a similar mechanism as well. Those are a few like mount options for F2FS. Not going over all of the details here, you can check it later. This is more for reference. Yeah, there is, for example, this sync mode that when you write, that might be a good option for you to always enable. And important to mention as well that some of those options might be enabled by default, so you don't have to really pass them. Just check the F2FS documentation if you have any questions. So the F-sync mode in the strict, so that is the POSIX mode, the strict mode. The strict mode we always calls F-sync. Sorry, when an application calls F-sync, it will flush everything, making sure that the device doesn't cache the writes. Because remember that F-sync will make sure that the caches in the kernel are flushed to the device, but will not make sure that the device is not caching that. So the F-sync mode strict will make that sure. Pretty much important if you want to ignore the caches from the device, right? If the device has any protection to power failure. There are also a few extra F2FS knobs that you can use. For example, you can force a checkpoint if you want. That's usually not needed because when you sync, for example, when you call F-sync, a checkpoint will be created. But if you want to do that anyways, there is an interface for that. You can check the states of the checkpoints. So there is a few extra knobs there. I would look at the documentation if you want some details. Yeah, and we have this huge MTD subsystem and UBI. I mean, again, I don't have much time to cover details here. But in a nutshell, managing how NAND device is hard. You have to deal in software with different problems, right? Where leveling, bad block management, bit flips, ECC algorithms, and so on. The kernel has a subsystem for flash-based devices called MTD. And you write drivers, MTD drivers for flash devices. And on top of it, you can run a file system. But of course, you will not use like XG4 on top of an MTD device because XG4 doesn't know about the underlying storage device. There are specific file systems for flash-based devices, right? The two most common are JFFS2 and UBIFS that runs on top of UBI. So UBI is a volume management layer that abstracts a few things from the flash device. It implements where leveling for you. It does some tracking of batch blocks. It has this concept of logical erase blocks, physical erase blocks, so you can, at runtime, create partitions, delete partitions that they call it volume, right? Logical partitions. So this is UBI, and on top of it, you run a file system called UBIFS. It is also log structure, so are usually not replacing files, but writing at the end of your log. And it was really designed to be tolerant to power failures. You can look at the documentation on some of the design decisions that they have. They have a journal as well. They basically checksum everything, data and metadata. You can replay the journal, I mean, just like X4. There are not that many mount options for UBIFS. Know what time. I'll avoid sync as well, as I mentioned. Try to control the syncs in the application. Only interesting option there is this SHK data CRC that can make it possible to check, to enable data the checking of data checksums. My time is almost over here, so I'm going to mention a few more things. For volatile data, TMPFS, always do in run. Duplicating partitions is another good technique because you can easily recover, especially for the operating system, right, the rootfs. And you can also use this if you have a remote update system. At the application level, you have to think about two problems. Reduce the vulnerability window, right? And make sure your writes are atomic. Those are the two most important things that need to care about. To reduce the vulnerability window, that means the time that the information is not physically in the disk. You might use fsync on critical writes. That would be one of the recommendations. To do atomic writes, that is a good technique. You create a temporary file. You write to this temporary file, sync the temporary file, and rename it. According to the POSIX standard, renaming the file is an atomic operation. So that's a good technique. Minimize writes. Avoid writing to the same file every time. Make sure the software that you are using do atomic writes. For example, if you are using a database software, make sure it supports atomic writes. Include checksums in your software. That's another good technique. So you can have checksums of critical files and check them. You can keep a redundant copy of critical files. That's another good technique. All of this at the application level. You can handle SIGTERM. That's the signal that the application will receive on shutdowns. So, for example, if you are able to implement a shutdown hook in your system, for example, using a PMIC, a power management IC, that notifies you on a voltage law event, you can integrate that with systemd. So you can have an I/O configured to generate the key power event, and then systemd handling that and shutting down the system this event. And then in your applications, you're going to receive the SIGTERM signal, and you're going to do whatever you want, like sync the operations. I mean, get into a good state before shutting down. So this can be integrated like from the kernel, from the hardware to the kernel and to the applications. There is some work that you can also do at the kernel level. So the regulator framework in the kernel has some support for you to register if you are implementing a driver that is a regulator consumer. You have a consumer regulator API that you can use to register for under voltage events. We have here the guy that implemented this. So yeah, not sure if we're gonna have time to discuss this, but that's a nice feature that you can have, for example, an eMMC controller receiving this event from the regulator and sending the command to the eMMC to flush the caches. Monitoring unintended reboots is also recommended. So you can have a simple file there in the file system. And when you boot, you check that file. If it's there, that's because you had an unintended boot. So the idea is that when you boot, you create the file. In the shutdown, you delete the file. So every time you shut down, you delete the file. If in the next deboot the file is there, something happened and the file was not deleted, then you can take actions. You can run tools, checks for errors, go into a recovery mode. That is one idea to handle unintended reboots. Recovering from corruption, it's hard, right? I mean, you can just refresh everything, but you might want to try to avoid it. If you have corruption in the operating system itself, usually this dual A and B partition is the best option. You can try to boot from a good partition. If the corruption is at the application level, you can have backups of important stuff. You might even try to factory reset the device to recover from corruption. But it is usually harder, so that's why we usually try to avoid corruption in the first place. But, I mean, in the end, there is no real solution for this. This is my final checklist. The slides are there, you can, but basically the summary of this presentation. I hope you enjoy it. It's really a step-by-step, on my opinion, on how you can design systems that are power cut resilience. Thank you.